It's time to enter the world of multicasting as we look at the concepts and configuration of multicast. Now, multicasting is a pretty big topic, and there is an entire series that is dedicated to multicasting as part of the CCIP certification track. But what Cisco intended to do was to introduce you to it in the BSCI world so you could get an idea of what it is and kind of the basics of how to set it up. Just like when you went through CCNA, you saw OSPF, but you didn't really see OSPF. It's kind of the same thing here. You'll see multicast, but just the tip of the iceberg. So what we're going to do is go through the major concepts that are important to you. The stuff that you'll want to know, why we do multicasting, how the addressing works, how you configure your switches and routers to support it, and the protocols that makes it tick. Finally, we'll wrap things up by looking at enabling a Cisco router to support multicast. Let's get going. Multicast traffic is one of those things that people hear about but don't really know in depth what it does. I kind of compare it to, well, email groups. I don't know if you've got corporate email, but in a corporation, if you're using like a Microsoft Exchange server, you have the ability to send people individual emails. I can say, hey, I want to send, Jim Shuitt this email, and it will go directly to him. It's kind of like a unicast email that's going directly to just Jim. Now, I'm sure you've also seen in the corporate email that you have the company list, meaning everybody in the company gets this email. And I've been in a couple corporations where that gets abused. Somebody, gets some goofy joke in their email and they forward it to the whole organization because they think, oh, everybody has to appreciate this joke. And so people just end up deleting spam out of their inbox. But inside of Microsoft Exchange and Outlook, you can actually create email groups. So for example, if I just wanted to send an email to all the accounting people, I wouldn't have to add them one by one to the list. I could just type in accounting and it would automatically put it into a group. That's the same thing that multicast does. In the network world, we have the ability to send unicast messages, meaning from one computer to another, broadcast messages, which goes from one to everybody, kind of like that spam where most people will ignore it and a few people will get it. And then there's the multicast, which is one to many or one to a group. The best way that I can demonstrate multicast traffic is by using, well, an application I used to use all the time. I used to teach heavily in the classroom environment, and I still do from time to time, but in the classroom environment, especially with Microsoft classes, every single week when a class is done, we would have to re-image all the PCs, pretty much, wipe them back to the original. Now, we would use this imaging program called, I believe it was Norton Ghost or ImageCast or something like that, and we would have this Ghost server in the front of the classroom. And that Ghost server would have all the images that the PCs would run. Now, Ghost can run in many different flavors. Matter of fact, you can configure Ghost to run in any one of these styles. If we configured Ghost to run in unicast, which is how we did it in the early days, the Ghost server would send out a single image stream to every single computer we were trying to image. And now, I don't want to take that for granted. When I say image, you know what that means, right? That pretty much means like wipe the computer out, put a default image like Windows XP back on there. Now, the disadvantage of using unicast was that we would have a classroom of like 10 or 20 PCs that we would want to be imaging. So the very first one that we added would be screaming speed-wise. You'd watch it start flying across the screen. Then we'd add the second one, and it would slow down. And then we'd add the third one, and it'd slow down even more. And the more we added, the more it would slow down until eventually you'd look at the time estimate and it's saying, it takes about 20 hours to complete this image because for every single computer, it required a unique stream. So it really divided the bandwidth that the server had available on its network card right there. So the alternative that we configured Ghost for was broadcast, which is where the server would send one image stream out and everybody would get it. Meaning, these three computers that I needed to image, and even these two computers over here that I didn't need to image. So the good news is that it was becoming more efficient because the server only had to send it one time and all these devices would get it. But the bad news was that the network just started performing terribly. The computers that didn't need to get the image, you'd open a web browser and just be crawling along. You'd have collisions. It would just be a nightmare because machines that didn't need it were just getting this image, and it would actually slow the whole training center down. So we eventually started using multicast, which allowed the server to send out one stream and just a group to tune into it. Now that's kind of how I describe multicast is I kind of describe it like a radio station. You've listened to the radio, I'm sure, and you have these stations that you can tune into. Now, the station's always there, right? It doesn't matter if you're listening to it or not. It's there. It's just not being received by your car. But when you turn on the radio to tune into the radio station and put it on the right frequency, aha, now we hear the music coming through our speakers because we've tuned into that frequency. That's how multicast works. Is, for instance, the Ghost server, and this is kind of a now it breaks down a little bit because Ghost is a application that wouldn't do this, but it's always sending a stream. Think of like internet radio. It's always sending a stream, and your computer can tune into that stream, meaning listen to the frequency. But instead of a frequency, it's actually an IP address. I'm getting in depth into the how multicast works, but that's really how it works. So the last point that I have on this slide is that in IP version 6, in the next version of TCP/IP version 6, there is no such thing as a broadcast. It's almost unfathomable because that's almost the foundation of everything networking is these broadcasts, and that's what we stop with routers, right? Well, in TCP/IP version 6, there is no broadcast concept. Everything has become multicast. So you can see how multicast is really gaining importance in the future. Now let's get into the facts about multicast. Multicast is all UDP based. That means there is no reliability built into multicast traffic. There is no windowing, like TCP windowing, that can tell somebody to slow down or speed up if you got more bandwidth available. It just sends it in the hopes it gets there. It's a steady stream. So any application that uses multicast has to have the ability to handle all of those errors itself. It needs to be able to handle if it's not receiving information at the speed it would expect. It needs to be able to handle if certain packets get dropped and be able to recover from that. It even needs to be able to handle when duplicate packets come in case something got looped around. You don't want the application to crash. So everything in multicast is unreliable, and everything uses a Class D address. Now, if you've played in the Cisco world for some time, I'm sure you're very familiar with the Class A, B, and C. It's everything subnetting and everything addressing that we do for our networks. But Class D addresses are usually untouched by most networks. You can see the range right there. Those are all reserved for multicasts. Now, here's where the concept really comes in. Workstation using multicast applications will subscribe to the server's multicast address. It's like these three computers. It's the same image I had in the previous slide. These three computers maybe want to receive from the server. And let's say instead of Ghost, this is internet radio. Okay, so we actually have little music notes coming out into the network right here. Now they will be sent to this essentially from that source address, 225.150.30, which is something from the multicast range right here. Now, the PCs, when they open their internet radio application, will send a request out to a router typically, but I've got a switch here, saying, I would like to tune in to 225.1.50.30. I want to hear that frequency. And at that point, that is now a subscriber to that frequency. The server is sending this out, coming from that source address, 225.150.30, and the switch is allowing the PCs that have sent the subscribe messages, it's technically called the join message, to subscribe to that frequency to receive it. When a workstation closes their application, they are now unsubscribed from that frequency, and the switch or router stops the stream. So it does not receive that flow of traffic. These computers over here that never opened their internet radio application did never subscribe, and thankfully, the switch will completely isolate them from the stream. It's not like a broadcast application to where everybody gets it and only the people that need it receive the packets and everybody else drops them. This is one that can truly choose what people or what PCs belong to the multicast group. So multicast addresses work a little bit differently than IP addresses as we typically know them. When you have a IP address and it's assigned to a host, whether it's public or private, that is the host's IP address. When it communicates, it says, hello, this is me, and people send back to that address. That's how network communication works. With the multicast address, I'll go back to my original analogy, it's more like a radio frequency. A lot of hosts can share the same address because they're not really assigned that address, they're just tuned into that frequency. Up till now, I've been using applications, multicast applications like Ghost or Internet Radio, and that is a server sending to a bunch of clients. But multicast can also support easily many-to-many communication, to where you have a bunch of quote-unquote servers that all send to each other. Let me give you an example. Video conferencing, where you have, we'll say, 10 people on the same conference call. In that case, we can use multicast to send one stream to and from each client, and every client that's on the video conference call is a server as well. They are sending a video stream, that is themselves, to everybody else, and receiving video streams from everybody else, because they're all sending and receiving the same radio frequency. They're all tuned in. So we can do many-to-many addressing just by all sharing the same radio frequency. So let's look at the specifics. First off, in multicast addressing, the entire 224.0.0.0 range is reserved by IANA. The powers that be that assign addresses say that is blocked off and reserved. Now, I should mention, you might look at that and say, wow, they took a whole Class A chunk. That's kind of a /24 if you're looking at that. It's kind of a Class C style range. So 224.0.0.0 through 224.0.0.255 is reserved. And I put the URL to see what applications are actually using that range that they have reserved. I put some well-known multicast addresses right below that. 224.0.0.1, if you send to that address, all multicast capable systems on the subnet will receive it. I want you to envision that as the replacement for what's known as a broadcast nowadays. I know you may have been thinking on that initial whiteboard that, hey, wait a sec, if there's no broadcast in IP version 6, how do we do it? There you go. It's just a multicast version of a broadcast. Now below that, you see 224.0.0.2 goes to all multicast capable routers on the subnet, and the clients don't actually receive that. Below that should be familiar because we talked about some of those earlier in the series. OSPF 224.0.0.5 and 6 is all routers, and then the DR and BDR. RIP version 2 is the .9, EIGRP is the .10. So those are the frequencies that those routers are tuned into, and that's what allows them to communicate without bothering anybody else. The last one I just threw up there because I don't know. I was looking at the RFC, which is right here. You can see these are all the addresses that are reserved. And I saw this one, tribal voice, that just sounded really cool. I don't know what it is, but I just thought I'd add it to the list to trigger your own curiosity. And don't worry, I already Googled for it. I don't know what it is, but it sounds cool. But those .0. something addresses are reserved by the IANA. And I did want to point out that there are other reserved addresses as well. You can see 224.0.1, and that list is completely thrown out there at that URL that I have at the top. So now let's move back to the original multicast standard that was written back in the day that TCP/IP version 4 was being developed. They spec'd out this thing called a global range, which is 224.0.1.0 all the way up to 238.255.255.255. What that was designed for, think global and think of your NAT terminology, NAT global addresses. These were supposed to work on the internet. You can see my little quote unquote supposed to work on the internet. It was originally designed or spec'd out that we would have this thing known as the M-bone, the Internet Multicast Backbone, which would eventually enable all routers across the internet to support multicast. And that would allow us to do multicast from our homes and from our places of employment and all of that because it would be an internet-wide thing. Well, if you go on Google and search for M-bone, it won't take you long to find out that it's dead. Not completely, as in the technology is gone, but it's just people are pulling back from it because it never really got the traction it wanted. First off, they never grew it much beyond 224.0 or actually 224.2.0.0. They just used kind of one class B range. The problem was that it was sort of a initiative that started happening. A few universities and ISPs picked it up, but because it wasn't required, everybody didn't pick it up. And if you did pick it up, what that would mean is a pretty significant hit to your bandwidth. So the multicast backbone sort of never grew enough to support multicast applications, which are typically very bandwidth hungry. You know, think Ghost, think streaming video, streaming radio. All of those things eat up a significant amount of bandwidth. So on the multicast backbone, when people started using it, they found that the bandwidth was constrained and they could never really grow beyond. So enough about the M-bone. It was supposed to work, it didn't, and so we have all these multicast addresses all the way up. You can see that all those almost class A chunks that are just essentially unused that were originally designed for the internet backbone. Those were supposed to be assigned dynamically. The vision of the N-bone would be that you would connect with a multicast application. And just like DHCP, you would sort of get a multicast address to use for your session. And when you were done, you would give it back, and that would be all hunky-dory. But again, the M-bone never really took off. So the range that we mostly will use in our organizations is that second one. The private range, 239 dot anything, is considered a quote-unquote private address, which you can use within an organization. It's an exact parallel to the private addresses we use for our IP addresses. These are addresses that route fine within companies, but when they get to the internet border, that's where they stop. The internet will filter them out. So you can assign those statically to your applications that are using multicast within your organization. As a fun side note, check out this website. Go to www.multicasttech.com. What this is a website that will allow you to see if your service provider or wherever you're at right now, your company or whatever your location is multicast enabled. If you look at this website, right here near the top is multicast text tester. And if you click on that, we'll come up and say there's a simple tool, choose to grant always. It's going to install some little plugin. But when you click this, oh man, I'm getting my little grant always thing. It's testing my multicast capability, making sure my ISP can run it, and denied. So this should, this will be able to tell you if you really are able to receive multicast or not. Chances are you're going to get the same message I did, but it's still fun to look. So that's multicasttech.com. All right. So with that in mind, let's get deeper into the multicast world. Multicast has its own set of protocols that makes it tick. The most important of all those protocols probably is IGMP, or the Internet Group Management Protocol. What this protocol does is allow a client to subscribe to a multicast stream. So let's say that we have some server out here in the middle of nowhere, right? That is, we'll say, streaming internet radio. This client finds out about that server. Now, there's many ways that it can do that. It could be from a web page. The web page has a URL that refers it to a multicast address. Maybe it's through some custom application that was created. Anything that can refer you to a multicast address is a valid way that you can get there. Now, when the client gets the URL or the referral, the application will realize it's accessing a multicast address because it's a part of that Class D range. And so an IGMP request will be sent to try and subscribe to that stream to gain that frequency on this workstation. Now, before I go any further with that message, there have been 3 major versions of IGMP, 1, 2, and 3. 2 is currently the most popular because 3 is still not quite baked yet. It's a draft standard on RFC. It's going to get there. It's just not there yet. Let me first off talk about IGMP version 1. The way that worked is this would send out an IGMP version 1 request, which would reach the default gateway or the router. Now, it's the router's job, if it's a multicast capable router, to try and find that stream. It's going to do, we'll look at the routing a little bit later when we look at the routing protocols, but it's going to do something known as reverse path forwarding, which allows the router to figure out the best way to the source, of that stream, which obviously took a right-hand turn in the road there. To the source of that stream, it'll try and find the best way to that server and subscribe to it. Now, in IGMP version 1, the server would respond and the router would start to play that stream to the client. And the client would be listening to their internet radio. And the router, every so often, would just send a kind of a check message. It's called a query message saying, hello, is anyone out there still listening to the stream? And the client would respond and say, yeah, that's me. Yeah, that's me. You know, at every X amount of time, depending on the implementation, the router would send out a query and just say, are you still listening? Are you still listening? Well, let's say that this client closed its internet radio. Well, the router would continue to listen to that stream. The server would still supply it. The whole, you know, there could be 50 routers in between here that the server's going through to send that stream to this router. And the router is still sending it over here to the switch. It's just no clients are responding to it anymore. The next interval, the router will send out a query message saying, hello, is anyone out there checking on this stream? The client does not respond and say, I'm listening, and it says, oh, you must be done. So it sends a close message and stops that flow. That goes the whole way up. All the routers up there would eventually stop their streams because there would be no further clients listening to that message. Now, the problem with that is just it's not efficient because with the query message, I mean, the router could close or the client could close, and then you're just sending nonsense, you know, traffic that doesn't belong there for a longer period of time. So IGMP version 2 did a few things, but the major thing that it did was allow the client to say, I'm done. They implemented what was known as a leave message. So the client, when it closes its application over here, would just send a message saying, I'm done, leave message, causing this router immediately to say, okay, well, you're done. It will send one final query out just to make sure no one else on the LAN is using it, because if there is other people listening to the same radio station, it can't close the stream yet. But if nobody responds to the query, it's closed down. So that became much more efficient because you can close the bandwidth right away. The version 3, the main thing that it's done is allow the client to say what source they want to receive the multicast from. For example, you might have many different internet radio servers that are all sending the same stream out, placed in different, let's see, that'd be kind of like logical locations around the internet. So maybe there's one for North America, one for Asia, one for Australia, and you have them physically located to where they would be better subscribed to. Well, with IGMP version 2, there's no way that this client can really say which one of those servers it really wants. It's just going to be whichever one the router happens to get to fastest and has the shortest path to will be okay, which for most part is okay, but we need the ability sometimes with our clients to say, well, I want to get that stream and I want to get it from that server right there, 200.1.1.1. So when it sends the join message saying I need the stream, you can say join this frequency. We'll say 225.1.9.30 is our frequency, but I want to get it from that server. So the router gets that request and routes it to the correct server. That's the main feature of IGMP version 3. There's some other minor things that were implemented in version 2 and version 3, but those are really the ones worth mentioning. IGMP is the protocol that allows the clients to subscribe and the routers to respond to the subscription requests. Now, there has been one missing piece through this whole story of multicast. And that piece is where's my pen? Right here. Did you know that switches, when they receive multicasts, treat them just like they do broadcasts by default? Meaning, as this supposedly super efficient application of streaming radios coming in, we're thinking, oh, this is great. Only the clients that need it are getting it. It hits the switch, which is not configured for multicast, and everybody gets it just like a broadcast, and only the client that subscribes to internet radio ends up responding. That's why we have these two additional protocols that have been introduced. Well, I shouldn't say protocols, they're sort of methods. The first one is the easiest, Cisco Group Management Protocol, and as you might guess by the name, it is proprietary. Here's what happens. The client opens that web browser and subscribes to the internet radio or whatever stream is coming in via multicast. The router responds and sends that through, but as it does, it also sends a CGMP message to the switch that says, hey switch, there is a client that you are going to be responding to, and they're going to have this new MAC address, because whenever you subscribe to a multicast frequency, you get a second address that correlates to that multicast address. There's actually a process it goes through to convert a multicast address into a hexadecimal MAC address that your workstation ends up getting. And so the router tells the switch, the client that just came in will have this new MAC address, and send it out that specific port. So the switch will assign the multicast MAC address to that port and then just filter it out right there. So that's a beautiful way of allowing the switch to become multicast aware without being a full layer 3 device, meaning a layer 3 switch, and communicating efficiently using those multicast messages to the client. So that way is the best, but of course requires Cisco devices everywhere, Cisco router, Cisco switch, in order for that to happen. Now, I do have that question of why would you have anything else, but I realize some people do. So there's a second method that's a little more industry standard. It is IGMP snooping. IGMP snooping allows the switch to start seeing the IGMP requests, meaning the IGMP join messages and query messages and leave messages and everything else that deals with the IGMP. Now, it may sound like, hey, that's definitely the best way, because it doesn't even take the router communicating with the switch anymore. The switch can just see everything happen. Well, there's a problem. IGMP messages are very plentiful, meaning if you have hundreds of clients that are all subscribing to a stream, maybe it's a corporate-wide broadcast from the CEO, then that's going to be hundreds of messages hitting that switch every moment. Now, switches are designed to work at layer 2. They're designed to work at wire speed using ASIC hardware. But if they're having to snoop and inspect every single IGMP message that's coming across, and there are lots of them, that's going to slow the switch down. So you end up with, number one, a major processing load on the switch, and number two, in order to do IGMP snooping, this switch must be layer 3 aware, which means that you have to buy a layer 3 switch, which means you're paying a lot more for that device than you would typically just pay for a layer 2 switch, like a 2950 switch that Cisco supports. So whereas IGMP snooping may sound like the better method, it really isn't in the long run. And if you can get by using CGMP, the Cisco proprietary one, that's usually the better way to go. The final concept that we'll talk about is the world of multicast routing protocols. You may not know this, but your normal routing protocols don't work for multicast. OSPF, EIGRP, those are unicast routing protocols. Multicast has its own group of routing protocols, and before we get into the specifics, you have to know the two major categories that they fit in and kind of the concepts around them. You can see over here on the right-hand side, we have source trees and shared trees. These describe the two ways that multicast builds its routing table, essentially. With the source tree concept, every single router tracks every multicast source. So let's say this guy starts streaming some audio. It's going to build a unique table entry and say, okay, for the source, 10.1.4.50, comma, and it'll put the multicast frequency it's broadcasting. We'll say 224.1.1.90 or something like that. This is how we get there. Then it will come down here to this router. Maybe this tuned into the multicast frequency. This router will build a unique entry for that 10.1.4 address, comma, and its multicast frequency, and stream it down here. Now remember, every multicast client is a potential source as well. So it will also build a unique entry for this guy, 10.1. let me get my pen here, 10.1.1.50, comma, same frequency. And every single router along the way, as more people tune into that, it will build unique routing table entries saying, okay, to reach this one, we're going to, or I should say, to reach this frequency, we're going to go to this source address and reach it that way. Now, it seems kind of weak to explain it that way, just kind of like, oh, okay, you got this source and you got this frequency that it adds as its multicast routing table, until you realize that the multicast quote-unquote routing table relies heavily on the unicast routing table. So it's just a list of saying, okay, this source right here and this frequency, this source and this frequency. But all of those are relying on the unicast routing table. It's saying, okay, this guy is tuned into it, but how do I reach that guy? Well, that's when it goes back to the unicast routing table and finds the path to that source. One of the unique things about multicast, and I've mentioned this before, is instead of worrying about the destination, we're worried about the source. Everything is coming from this source. Everybody's trying to find the best way to reach that source. So when we're talking about this client tuning into the frequency, it's really using the multicast routing table to try and find the best way back to that source, 10.1.4.50, which then looks at the unicast routing table and says, well, what's the best route to get there? And it finds the best path back. Now, without skipping a topic, I'll come back to shared trees. I want to go right into it because that is the concept of reverse path forwarding. As the multicast routing table is built, RPF, or this reverse path forwarding, will ensure that there's no loops in this frequency. You can imagine as different devices tune into the, we'll say, streaming radio that the server is providing, there could be a potential of loops in the network. And what RPF does, or reverse path forwarding, is it tags the interfaces that the frequency is coming in as. It's looking up in the routing table saying, okay, what's the best way to reach this 10.1.4.50 server back here, and it looks and it says, well, the best way to get there is out serial 0. So it builds a reverse path table to that server. And if it ever receives any incoming packets that are streaming from 10.1.4.50, that source, maybe it came down here and streamed down here, and it's coming in an interface that is not the best path back to that server, it will drop the packets. That's its loop prevention mechanism, is it's always looking for the best path to reach the sources. That's why they call it reverse path. And then if anything comes in on a different path than that reverse path, it's assumed to be a loop and it will be dropped. Now, the last concept I want to show you as the categories of routing protocol is the shared tree concept. You can see that as the second one right here. In the shared tree world, we've moved into a world where the clients and multicast servers have become much bigger than just a source tree world. Source tree, I should mention the benefits. In the source tree world, the benefit is it's very easy to set up. The routers kind of discover the best way around the network, and they just kind of keep track of all the sources and build their best way there. And we'll see some more of the advantages, disadvantages of that when we look at the specific routing protocols. But as your network gets bigger and bigger, and as more people start tuning into those multicasts, the routing table for the multicast world gets extremely large. And every single router has to find the best way back for every single unique source, and it becomes inefficient. Routers start getting their resources consumed too fast. So in the shared tree world, what we do is we elect one router as this thing known as the rendezvous point, or RP router. What that is the central point of contact for all multicast signals. So essentially, everybody is going to go through the rendezvous point. So when this server starts streaming, it's going to stream down here to the rendezvous point, and then all the clients will come to the rendezvous point to find that signal. So essentially, instead of the routers keeping track of all the sources and the frequencies that they tune into, you'll see entries in the multicast routing table that has a little asterisk, comma, and then the multicast frequency, 224.0.0.9, I'll say. Now that's RIP, but we'll assume that's the frequency for now. What that little star is it's saying, I don't care what the source is, we're sending everything back to the rendezvous point. And of course, this router has to be configured with the address of the rendezvous point at that point. at that point. Huh. So when this guy tunes into the frequency, the router says, oh, let's go check with the rendezvous point. And the rendezvous point says, I've got it, and then starts streaming it down here. Now, the benefit of using a shared tree, that's what the category of routing protocol is that the routers don't have to keep track of every single source and what the best path is for it. So the efficiency goes up because the multicast routing table is very small. The disadvantage of using the shared tree design is that you may not get the best path for everybody. You notice I chose that middle router. I kind of drew my diagram this way for a reason. I chose that middle router as the rendezvous point because it's in the middle. Everybody's kind of close to it. But you can imagine that maybe you have a T1 line right here and maybe a 512K connection here and I'm trying to find a way to make this extremely inefficient. The point is maybe you would come down here. The reason my example isn't working out here is because the unicast routing protocol is going to say, oh, that's a better link. Let's go that way. So I was trying to think of making that a very bad link too. But then we just got bad links all around. I'm digressing. The point is that you may end up having to go a longer distance to reach the rendezvous point than you would to reach this original source. Does that make sense? With the source trees, this client is going to find the best way to that server, period. But with a shared tree, you may have extra hops in between because the rendezvous point may be a little further away than the original server is. There it is. So that's the two categories of routing protocols, source trees and shared trees. Now to the specific protocols. You can see them on the screen, PIM dense mode and PIM sparse mode. Now, before we get into the details of those, let me tell you, there are more multicast routing protocols out there. There's even a flavor of OSPF that does multicast too. But the two that Cisco elected to put in the BSCI world was the two PIM modes, that stands for Protocol Independent Multicasting, because they're the most popular. They're the ones that most people use. Very, very easy to set up. The two strategies look like this. If you choose PIM dense mode, you are choosing a source tree algorithm to where it's going to have the bigger multicast routing table but can find the best way to get there. Now, the beauty of PIM dense mode is it's kind of like RIP. You just turn it on and it works. Here's the concept. Once I enable all of these routers for PIM dense mode, let's say this guy starts streaming. He starts streaming in streaming audio radio. Immediately, these routers will flood the whole network. They will send that stream everywhere on the network to see if anybody wants that stream. Now, as the routers realize, hey, I've got no clients for that stream, they realize that with that IGMP, they're going to send back prune messages saying, nope, not me, not me, not me. And so it kind of prunes back to the source. And then after a certain interval again, the router floods the network with the multicast and says, hey, I got the multicast, and here you go. And everybody's like, nope, not me, not me, not me. So they kind of prune it back as it goes. And that process continues until the source shuts off its stream, because it's always going to continue that for the multicast traffic. Now, I know that sounds like, oh, that is unbelievably inefficient. And it is, but it's not as bad as you think. As soon as it sends out the stream, immediately the router's like, nope, sorry, I don't have that. So only a few packets get by. And the beauty of PIM dense mode is it's so easy to set up. You just, like I said, turn it on and the routers will start working. So if you're looking for a zero-brainer kind of configuration, PIM dense mode is the way to go because you just enable it. PIM sparse mode is the shared tree algorithm. That is the shared tree routing protocol. In that mode, we specify a rendezvous point. That's where we say this router will be the rendezvous point, and then all the other routers have to be statically configured to go to that rendezvous point. Now, there is this concept called auto RP, where they kind of auto discover the rendezvous point, but even that takes a little more setup. So PIM sparse mode, being the more efficient of the two, will designate that rendezvous point, and all routers will point to that, and it does not flood the network like dense mode. It just, as it receives requests, it will send it to the rendezvous point, and the rendezvous point will go acquire the stream and send it to everywhere else. So those are the two major multicast routing protocols that exist. I was going to create a separate multicast configuration video for you, but then I thought about it and thought, there's not much to it, really. Here's the idea, at least with the basic multicast model. I'm going to do a show IP interface brief real quick, just to see that I've got some active interfaces here. Let me go under one of my serial interfaces, serial 0/0.1, and do a no shutdown to power that on. So, two commands if you're setting up the dense mode. I'll show you how to turn on multicasting and set it up for the PIM dense mode. You go into global config mode, and the number one command that you'll want to remember is this: IP multicast routing. Enter. Unless you type that command, the router will drop all multicast packets that come to it. It's kind of like, I don't know if you remember back to the old Cisco routers when, or I should say old iOS versions, when you would first get into the router, it wouldn't route. Even if you gave the interface IP addresses, even if you turned on routing protocols, it wouldn't route until you went to global config mode and typed in IP routing. It's kind of goofy, but now that's a default command on every new iOS version that's out there. Multicast, however, is not a default command. So you need to go in, just like we typed in IP routing for the unicast world, and type in IP multicast routing for the multicast world. Now, all you've got to do is tell it which interfaces will participate in multicast. The way that we do that is going under each individual interface. I'll go under serial 0/0.1. And now I get to choose what kind of PIM mode I want to run. IP PIM, and I'll hit the question mark. And you can see, quite a few options, but the big ones are dense mode and sparse mode. Now they also have this sparse dense mode, not really talked about in the bsci world, but what that is it runs both flavors of the routing protocol. It will send the multicast out and then prune it back just like the dense mode always does, but it can also be configured for a rendezvous point. So that way, if you're unsure as to what the other routers are running, you can run both until you discover it and then choose one or the other. So if I'm using dense mode, that's the second command. IP PIM dense mode. Enter. I was waiting for some sort of music to play or fireworks to shoot or something, but that is all there is to multicast configuration, at least if you're doing the dense mode. Because at that point, as long as serial 0/0.1 is your interface that connects to the multicast areas of your network, that's all the router will begin routing the multicast. Now, obviously, this router will probably have other interfaces that need to connect to the multicast world, maybe even all of them if you do multicast network wide. So you'll have to go under each interface and type in IP PIM dense mode, otherwise it won't work. Now, if you were to use sparse mode, let me drop back out and show you the commands you'd have to type in to specify the rendezvous point. I love the question mark at global config. It is IP PIM. I'll hit the question mark, and right here is the rendezvous point address. And that's where you can type in what rendezvous point you would like to configure on this router. Also, I kind of digress a little bit, but multicast is pretty cool. You can see this send RP announce and send RP discovery commands. What that does is allow the auto RP process to take place so that it can go in and send discovery messages saying, if I am the rendezvous point, hey, discover me. And you can see, or sorry, I did that backwards. The RP announce is on the rendezvous point saying, hey, I am a rendezvous point. This is my announcement. You also have the RP discovery, which is done on every other router, that allows them to go out and find the rendezvous point who's announcing itself. Of course, when you type that in, you'll have to type in send RP discovery because that's their little discovery packets. You get to say what interfaces and what scope it will go out, meaning how far do you want to try and discover the rendezvous point before it's a lost cause. You'll want to scope it as far as the routers go within your organization. You don't want it kind of bleeding out of your organization trying to find a rendezvous point. And that scope, by the way, is in hops. There is much more we could talk about in regards to the world of multicast, but at least at the BSCI level, this is all Cisco wanted you to have. Since there is an entire certification track, CCIP, that gets heavily into multicast, there's an entire multicast exam. So for now, what we did see is why multicast is important to you, which we're going to see more of that when we get into IP version 6 in the upcoming videos. It is important because it is your one way that you have to send one message to many receivers without flooding the whole network with broadcasts. We looked at the facts about multicast, kind of a laundry list there, and IP addressing in the multicast world, where we went through the Class D addresses and how they work and how they're not just a single address like our normal Class A, B, and C addresses. They're more of like radio frequencies that you tune into, so many hosts may be sort of sharing the same multicast address. We looked at multicasting, and this is a lot of stuff. Multicasting in the layer 2 and 3 world, because switches have to participate as well. Otherwise, they will run into the problem of treating multicast as broadcasts. So we have IGMP that is used to signal and start the multicast streams. We also have CGMP, which is the Cisco proprietary method that the routers use to notify switches about multicast. Also in there, we talked about the routing protocols of multicast. A lot of stuff. Finally, we looked at the enabling a Cisco router for multicast. We saw the key command IP multicast routing from global config mode. And then we got into the IP PIM sparse mode and IP PIM dense mode options that we have for routing protocol. I hope this has been informative for you, and I'd like to thank you for viewing.